you everyone for attending today's Foxconn Quantum Computing Seminar. We have the pleasure of having Yanglin Hu, who will tell us about sample-optimal and memory-efficient quantum state tomography. So Yanglin is a PhD candidate, so he's about to finish his PhD in the Center for Quantum Technologies at the National University of Singapore. His research focuses on two main topics: multipartite quantum cryptographic primitives and applications of Schur duality in quantum information theory. Yanglin obtained a master's from ETH Zurich and a bachelor's in physics at Peking University. So Yanglin, the floor is yours.
Okay, thanks. Thanks for your nice introduction. So today I'm going to talk about this unitary Schur sampling with applications in state tomography. So originally I wanted to talk about sample-optimal and memory-efficient state tomography, but because that paper because we have a contemporary paper and they have very close relations, so I decided to talk about both papers together. So these are two papers. One is this paper and another is this paper. So this is a work with Enrique Severo, Laura Masinska, and Elias Sell, and also my supervisor, Marco Tomamikel. And right, so maybe let me gradually start. So the first part I talk is about unitary Schur sampling. So in many quantum information tasks, you will get you will receive input. There are m different states like row 1, tensor row 2, tensor and tensor row n. And sometimes the order of the input is irrelevant. Maybe I could give you some example, like you want to estimate the spectrum of you want to estimate the spectrum of a specific state, and you are given the state for n times. And sometimes you want to do state tomography. That is, you construct a classical description of a specific unknown state row, and you want to use n copies of the state to do this. And also sometimes you want to do cloning, like you have n copies of a certain state, and you want to maybe put them into a cloning machine, and such that you will get approximately m copies of the same state. So these are some examples where where the order of the input is irrelevant, and you have some permutation symmetry between those n copies of the state. And in this case, we could use this permutation symmetry to simplify our task. So this motivates us to understand the action of the symmetric group on the n copies of Hilbert space. Okay, so this is why we are motivated to understand the action of permutation group. So then a very important theorem to understand the permutation group is the Schur duality. So basically, the Schur duality says that the n copies of the Hilbert space, it is equivalent to the direct sum of a bunch of subspaces, where on each subspace it is in a tensor product form. So maybe I could turn on my right. So it is a tensor product form. So it is a so on each subspace is denoted by some lambda. Maybe I just call this lambda the label for the subspaces, and on each this subspace it is in a tensor product form, p lambda tensor q lambda, where this p lambda is the representation of the permutation group. That means the permutation group only acts non-trivially on this p lambda subspace, and this q lambda is the irreducible representation of the unitary group. Also, it's a irreducible representation of the general linearized group. That means for any for any like U for any unitary such as U tensor n, it only acts on non-trivially on this Q lambda D subspace. So basically, this P lambda subspace, the symmetric group acts non-trivially on this P lambda subspace, and the unitary such as U tensor n acts non-trivially on this Q lambda subspace. Okay, so, and maybe I just give a more introduction on this lambda. So this lambda, it has a so-called integer partition of n with at most d elements, where d is the dimension of each Hilbert space. So basically, you can write this lambda as lambda 0, lambda 1 until a certain number, such that this lambda 0 plus lambda 1 plus until plus lambda d, they sum up to n. Or you could write it as so this lambda 0 should be greater than or equal to lambda 1, should be greater than equal to lambda 0, lambda 2 until lambda d. Okay, so you could also kind of give a diagram representation of this label lambda. So you could draw a diagram such that in the first line you get lambda 0 boxes, and in the second line you get lambda 1 boxes, and the boxes in the next line is no more than the boxes in the previous line, and in total there are n boxes. Okay, so this is the label for the Hilbert space. It is given by something like this. Okay, so this is called a partition of the integer partition of n. Okay, so now maybe we can look again at our symmetric input row tensor n. So remember that in the Schur duality, the general linear group, like a matrix tensor n, it is only non-trivial on this on the irreducible representation of the linear group. So it is only non-trivial on this Q lambda d. Okay, so now we can write any row tensor n in the form of this guy, where you can decompose it into two parts. One is so it has a direct sum of all the lambda subspace. You can think the direct sum of this lambda subspace as some sort of a classical register. And then there is a identity matrix on the P lambda subspace that is the irrep for the permutation group, tensor product, the irrep for the unitary group, and the general linearized group, general linear group. Okay, so now you see that because there is identity on this irrep of permutation group, so so there is no information here, and all the information about the state row is in the irrep of the permutation group. Okay, and this holds for any symmetric input state, and we can use this to kind of do tomography and to help do our task. Okay, so basically what we can do in order to for example, to do tomography is we first measure this lambda, we measure this classical register and get a classical lambda, and then we can we get a identity tensor Q lambda d row, and because this identity contains no information, what we can do is we discard this identity part, and what we get left is just this Q lambda d row. And this is what we call the unitary Schur sampling. So for an input state on CD tensor n, the task of unitary Schur sampling is equivalent to first measure the irrep label lambda, and then we just discard the permutation irrep, and then we return the reduced state on the Q lambda d subspace. So this is what we call the unitary Schur sampling. And to do this unitary Schur sampling, we can use the so-called Schur transform. So this Schur transform is a unitary which maps the U tensor n input state into the direct sum of into 3 registers. The first register is kind of the classical register, which records the lambda, the irrep label of the subspaces, and then you get a tensor product of the p lambda subspace and the q lambda subspace. And to do unitary Schur sampling, we can just discard this p lambda subspace, and we measure this lambda label. Okay, so in order to do the unitary Schur sampling wisely, there is another theorem, which is we call it the branching rule. That means suppose if you initially have a q lambda subspace, and then you append another ancilla that is in the C tensor D subspace, then it's kind of like, so suppose now you perform the unitary Schur sampling on n, maybe on n qubit, and then you get you get a state on q lambda subspace. Then you can append an additional row state, and you can maybe do some calculation on row q lambda d and the additional state row. Okay, so this is so then you can use the branching rule, which means that q lambda d, this subspace, tensor another new fresh state on the on CD Hilbert space. This is equivalent to the direct sum of another bunch of q mu subspace, where this mu is the original lambda, and you put another box on it. So maybe let me illustrate this more. So suppose this q lambda is a rep labeled by this label lambda, and when you append a new maybe CD Hilbert space on it, then this is equivalent to so this decomposes into a bunch of these subspaces, where in the first one you could add a new box on the end of the first line without violating the rules for the partitions, and you could also append a new box here, like here, to get on the second line to get another new representation, and you could also append a new box here, like at the end, in the third line to get a new to get a new label. So basically, this space decomposes into this space. Okay, so this gives you a kind of recursive way to do the unitary Schur sampling. So basically, you can first do the unitary Schur sampling for 2 states, and then you get lambda 0. Sorry, then you get this lambda 1, and what you get is another q lambda, another state which is on q lambda d, and then you append a new quantum state on it, and then you do a then you apply a unitary on it, and you can transform this into this bunch of things, right? And you get the q lambda d for 3 qubit, and the lambda also for 3 states, and you can recursively do this until you get the q lambda d for n such for n such state, and also the lambda label for n such state, and also the p lambda space for n such state. Okay, so this is a recursive way to, yes?
Can I just ask a question about this? Is, you know, in rep theory, there's this kind of approach to looking at how representations of like bigger irreps contain smaller irreps, right? There's this way of studying these restrictions. Is this like exactly that process, or is it something kind of analogous?
I think this is something come out of it. So
okay.
Okay. So this is something come out of it. Right. Exactly. So maybe I continue. Okay. So yeah. So basically, this is how you do the unitary Schur sampling in a recursive way. And what we suggest is we can do this unitary Schur sampling in kind of a streaming way. So basically, so in this case, we have to keep all the things in quantum memory, but you see that you never touch this line and this line, and also this line after you use them, after you first use it. So this motivates us to kind of do everything in a streaming way, so that, for example, we are facing the case where we get the input coming streamingly, and so we could once we get a new fresh copy, we can first do the the Clebsch-Gordon transform on those two. The Clebsch-Gordon transform is this UCG, and we do the Clebsch-Gordon transform on this two, and we produce Q lambda subspace for this corresponding to state, and then we measure the quantum register that we will never use anymore, and we just repeat this process for many times, and once we do not use a certain part anymore, we just make a measurement on it. In this way, we kind of only need to keep a much smaller quantum part, and all the other registers that will not be used anymore will be kept in classical register. Okay, so this is one way to kind of reduce the quantum memory we have to maintain. Okay, so maybe let me briefly compare it a little bit. So if we want to do the full unitary Schur sampling by keeping everything coherent, the register we have to keep is this. It is all the quantum register, and what we have is the rho p lambda subspace. This is a quantum state on the p lambda subspace. Tensor the lambda, where lambda is the label, and also the q lambda subspace on the subspace on the rep of the unitary group, and the dimension of this quantum thing is C tensor D, then tensor N. So it's D to the power of N. And the memory we have to maintain is the logarithm of this guy, which is N log D. Okay, and once we use the streaming for unitary Schur sampling, the only quantum register we need to keep is the Q lambda D register in each step, and the dimension of this Q lambda D subspace is upper bounded by n+1 to the power of dr, and the memory we have to maintain is only the logarithm of this guy, which is dr logarithm of n. Okay, so this is I have to mention that this is only an upper bound, so this is dr log n is only an upper bound, and this might not be a very good upper bound if, for example, if dr is smaller than n. So actually, if dr is smaller than n, we have another upper bound, which is d to the power of n. And when dr is when d is greater than n, then we have this we have this upper bound. This upper bound is better, right?
Okay. So what is the R?
R, so sorry, forgot to mention. So this R is the rank of the input state. So so this R is the rank of the input state. And,
I see.
Yes, thanks for asking. I forgot to mention this. Right, so you see that the dimension of this Hilbert space is actually it depends on the rank of the state. So if you have a low rank state, then you know that this dimension is very low. Okay, so that's it. So maybe we just compare all the previous algorithms and the streaming Schur algorithms. So previously we have a Bacon's algorithm on unitary Schur sampling. So their memory is n plus d squared, and the gate is n times d to the power 4, and for Crovey, the memory complexity is omega n, and the gate is polynomial of n. And in this work, well, the memory complexity is Rd, and where R is the rank of the unitary, and the gate complexity is n R to the power 3 times d. So you see that we have so when right, so you see that we get some advantage on them. So we get a exponential memory saving in n, and also the rank dependent in we get a rank dependent in we get a rank R dependent improvement of time complexity, which is R cubed divided by D cubed, and also we can also generalize this to the mixed Schur-Well duality. So for the mixed for the mixed Schur-Well duality, we just extend the permutation group into the Brouwer algebra. That is, we have some symmetry on the CD tensor n, and the conjugate of this CD tensor n space. So basically, we have the transpose of the permutation. Yes, we have the transpose of the permutations, and we see that our low rank speed up applies to both full Schur and mixed Schur transform. Okay.
Sorry, I have the definition of n and d. N is the number of sample.
Right, n is the number of qubit.
Number of qubits. And
Right.
what is d?
D is the dimension of the Hilbert space.
So I'm interested in the relationship between d and n. So could you tell me? I'm interested in the relationship between d and n.
Right. Right. So I think our algorithm will work better when d is when d is larger.
Thank you.
Sorry, maybe a moment. Sorry, I made a typo here. So our algorithm work better when n is large, like n is much greater than d, or so on. And because we get an exponential memory saving in n, so here we get a logarithm. So here we have high the polylog factor of n, d, and 1 over epsilon. So basically, when n is much greater than d, in that case, this Rd is much better than the n case, the n scaling, and if we don't consider n, then if we consider n is very small, in that case, they still have a d-square the d-square memory requirement, well, our algorithm have already decreased. We have get a R-dependent improvement, so our algorithm will work better for low rank states.
I think I understand.
Okay, thanks. So thanks for your question. Yes, so maybe so this is our streaming unitary Schur sampling algorithm, and maybe now we go to the next part. So basically, we want to apply this streaming unitary Schur sampling algorithm to the case of state tomography to find the real application of it. So maybe let me first explain the setup of the state tomography. So a typical state tomography algorithm, a typical state tomography scenario is we get an IID stream of the unknown state row, which is we get row 1, 2. We get it in the stream. We receive the state 1 by 1. And the goal is we want to produce an estimate row hat of the state row. Okay, so basically, what we can do is when we first take a state row and we put it into our quantum register, and we also have a quantum register keeping. We have also quantum register alive, and we put these two parts together, and we use the classical register to control measurement on this two on the new quantum state and the quantum register we keep. And after the measurement, we kind of discard part of the quantum register, and then we will again have we will have a live classical register and a live quantum register, and we will receive the next state and perform the new measurement to do it. Okay, so the size of the number of the number of states row we required to do tomography is called the sample complexity, and the quantum register we have to maintain during the during tomography is called memory complexity, and the time we use to do all the measurement is called is defined as time complexity. Okay. So maybe now I give a more formal definition of the state tomography. So in state tomography, we will receive n copies of a rank R state row, and the state is d-dimensional. Yes. Any questions? No. Okay. So the task of state tomography is to measure the copies of the input state, and then we produce a classical description row head of the state, and we want to ensure that the trace distance between the state row and row head is upper bounded by epsilon with a probability of 1 minus delta. Okay, so in our work, the goal is to first maintain the sample optimal, and then maintain the and then to make memory efficient, and then it's the time complexity. So basically, we are trying to optimize this sample optimal and the sample complexity and memory complexity. Okay, so there was a sample optimal state tomography that uses the symmetric, like the permutation symmetry. So remember that row tensor n, it is equivalent to this identity, this direct sum of identity tensor product, this row, this Q lambda subspace, where this identity contains no information on the state, and this Q lambda subspace contains all the information. So basically, a way to do this is we first perform a projective measurement on this lambda. Once we get this lambda will estimate the spectrum of the quantum state very well. And then the next step is we perform a continuous POVM on this Q lambda subspace, and the continuous POVM is proportional to this guy. Like it's so this lambda bar is just the spectrum of the state you estimate, and then you kind of rotate the spectrum you estimate with a hard random unitary, and to construct the continuous POVM, and then the measurement output of this POVM is U, and this U will estimate the unitary of the quantum state very well. So by unitary of the quantum state, I mean we can write any quantum state as rho equals to V times maybe mu times V dagger, where mu is the spectrum of the quantum state, and V is the unitary to rotate the to make the rotation once you get the spectrum. Okay, so combining both, you can give a very good estimation of the original rho by U lambda bar U dagger, and this lambda bar is the irrep label you get from the first measurement, and this U is the unitary you get from the continuous POVM, and you know, and you can make sure that the trace distance between rho and rho head is upper bounded by epsilon. Oh, sorry. Okay, so this is how you do sample-optimal state tomography. Okay, so the sample complexity is RD over epsilon square, and the memory complexity is RD over epsilon square times the ln of D over R epsilon. Okay, so and now we want to try to minimize. So based on this sample optimal state tomography, we want to try to minimize the memory complexity. So the way we do it is we want to use the streaming unitary Schur sampling. So basically, in each step of the calculation, we only we measure all the lambda, and we only keep alive Q lambda D subspace. And by using the unitary Schur, the streaming unitary Schur sampling, the quantum register we have to keep is only dr polylog of n, dr times polylog n times d, dr times a polylog factor of n and d, and the time complexity is only n dr cube times a polylog factor of n and d. Okay, so this is the quantum memory we have to use for the streaming unitary Schur sampling case, and we also need to bound the memory complexity of the continuous POEM. So in order to bound the memory complexity of the continuous POEM, because for continuous POEM, to measure it, you need a very large memory. So what we can do is we kind of discretize the original continuous POEM. So originally the continuous POEM is something like this. We can find a unitary design and to try to, we can find an approximate unitary design and we try to discretize it. So by discretize the continuous POEM by a discrete POEM, we can upper bound the element in the POEM, and that will give us an upper bound on the quantum memory we have to use. And we can, so the way we sample this unitary design is we sample from a hard random subset, and we prove that the so for each element of the set, we sample it from the from the hard random set, and the set we need the number of elements in the set is upper bounded by n to the dr times dr cube, and we show that this discrete unitary design it exists by some operator valued Chernoff bound. Okay, so we kind of discretize this continuous POEM, and we show that to perform this discrete POEM, we have a upper bound on the memory complexity. Okay,
sorry,
so
can I just
yes?
want to ask here, like, you're not using like a specific design, like a specific unitary design, you're just kind of proving an upper bound on like the existence of some discrete design, is that right?
Yes, yes, right. So we are proving the existence of the of this design. So, but we still offer kind of a construction of the design. So basically, you sample a unitary from the hard measure, and you repeat this, and you kind of make this as the first element of the unitary design, and then you sample the second one, and if you sample enough times, like n to the power of dr times dr cube, this many times, then you have a very high confidence that this is a unitary design. But of course, you can construct this set. Use some wiser way, like there is some recent progress on constructing unitary designs with a very low depth. So construct this unitary design efficiently. I think it's by Robert Huang. his recent. Yes.
There's like standard ways of doing this that are like fairly simple, right? Like, I mean, even like from a few years ago, there was this paper where you could just do like layers of Clifford and T-gauge, and very quickly you get a T-design. I'm just trying to understand why you're doing this rather than just using one of those off-the-shelf kind of methods for constructing a T-design.
Right. So a good question. So because for those methods, they usually have a bound on the T, right? If I remember correctly, for Robert Huang's method, you have to require T squared to be smaller than N. But here, we actually need a larger, a unitary T design with T larger than N. So from that sense, Robert Huang's method and some other previous method cannot be directly applied to this case. So does this answer your question?
Yeah, I guess so. So because your method is works really well when N is very large, you don't want something that and you need a T design that is order N, is that right? Or
right, that's
so
true.
you want something that doesn't depend badly on N.
Right.
Is that right?
Right. Okay. So from that sense, Robert's it doesn't work well in this case.
Okay, thanks.
Okay, so thanks. Right, so basically this is the proof sketch. We just select random unitaries from the Haar measure, and the expectation of this random unitary is identity, and then we can use kind of the Chernoff bound to show that the probability that after you sample n such unitaries, the average of this n elements is the probability that the average is not in this, it does not approximate the identity is smaller than this guy, and this indicate the non-zero probability indicates the existence of such a set. Okay.
Sorry, I'll just be a pain one more time and say, like, I guess it's not efficient to sample from the Haar measure, but I guess you could use like Robert's method or one of these other off-the-shelf methods to sample from a T design where T is at most as many as the number of samples you need here or something. And then everything will go through, I assume. Is that right?
Right. That could work. So we have not checked carefully, but again, it's for Robert's case, it breaks down when T is the square root of n. So so for our case, it's kind of T smaller than the logarithm of n. So sorry, T smaller than the logarithm of D. So so his method kind of breaks fairly quickly I mean, in the application of this case, his method breaks fairly quickly. So I'm not sure if his method can be directly applied here. But I guess that's a very nice. So his method is a very nice method that gives us some confidence that we can find some more efficient way to deal with it. Although it would be still kind of several steps before we could really find the method.
So I guess maybe then it's not clear that there is a kind of low complexity way of implementing this POVM.
Right, that's right. So maybe in the next page, I will introduce this case. So basically, for now, for our method to implement this POVM, there is a very the time complexity is very large, but we can indeed bound the memory complexity by dr logarithm of dr epsilon, which is in accordance with our previous memory complexity of the unitary Schur of the streaming unitary Schur sampling algorithm, but the time efficiency is indeed a very it is a very huge trouble. So and it is also unknown whether you can perform this type of POEM efficiently, even if you know the efficient way to sample sample U. Right. So even if you know how to sample U efficiently, it is still unknown whether you can perform this discrete POEM very efficiently. So there is another gap. Right. Right. So so we didn't optimize the time complexity, which is indeed very bad, the time complexity. But in this paper, we mainly focus on the sample complexity and the memory complexity. Okay, so maybe I just compare to what we had to some other previous work. So you see that we maintain the sample optimal, where we get like an exponential memory complexity saving with respect to the epsilon. So here originally it is so the memory complexity is 1 over epsilon square, and now we can put the epsilon into the logarithm. Okay, so we get a optimal sample complexity, and we get a memory logarithm in epsilon scale with rank R, and we have a similar result if we want to do tomography in terms of infidelity, where infidelity is 1 minus the fidelity between rho and rho hat. And we also show that the probable approximately correct condition is the same as second momentum of distance condition. This is up to a logarithm factor. Okay, so basically that's what we have done, and there are still some open questions. So for the unitary Schur sampling part, one open question we have is whether we have some applications for the unitary mixed Schur sampling. So so we have found some application of the unitary Schur sampling, but not the mixed one, because for the unitary mixed Schur sampling, you get the symmetry, that is the permutation symmetry, and also you get the permutations and also the transpose of the permutations. And in that case, it is no longer a group; it becomes an algebra, and many things messed up. And we also looked at like Robert's method to construct the unitaries efficiently, to sample hard random unitaries efficiently. We also want to so Robert Huang's method on sampling unitary efficiently, it relies on the property of the permutation group, and we can we wanted to kind of generalize this from the symmetric group to maybe some other group, like the Brouwer algebra, which is the permutations and the transpose of the permutations. But we failed to generalize Robert's method to those groups. And Robert visited us last week, and we talked to him. He also wanted to generalize, but he also failed. So this is some question on whether we can find some application for unitary mixed Schur sampling, or more generally, whether we can make use of the Brouwer algebra in some more elegant way. So this is one open question, and another open question is whether we can find some efficient algorithm in the case for n much smaller than d. So in our case, our algorithm has some advantage when n is much larger than d, but for n much smaller than d, our algorithm has very little advantage, and we want to find an efficient algorithm for this case. And some other open questions are like whether we can find an efficient way to implement the discrete POM construction. Right, so now we almost have an efficient way to sample unitaries from Haar random unit from Haar measure, but there is still a gap to kind of perform this discrete POM. There is still a gap between efficiently performing this discrete POM and sampling unitaries from Haar measure efficiently. So there is a gap, and this is a long-existing problem, and people have looked at this problem for a long time, but there is not much progress so far. And also, we could find a lower bound on quantum memory of the state tomography algorithm. This is also something we can look at. Okay, so basically this is the talk. This is all about the talk, and I'm happy to answer any questions.
Can I just ask? So, I just want to comment on this efficient algorithm for n much smaller than d. I guess in that case, like the Crovey algorithm is the way to go. Is that right? Because they're kind of everything's poly n, right, in the Crovey algorithm.
Right.
Yeah. But
right.
Is
that
there? Sorry, you go.
You go.
Is there any issues with the Crovey algorithm? I've heard, I've never really understood it, but maybe there's some potential problem with the strong Schur sampling aspects of Crovey algorithm and efficiency or something. Do you know anything about this or?
Well, the Crovey algorithm actually my my colleague Elias looked at it very carefully, but personally I did look at it very carefully. So maybe I am not the best one to answer this question. Okay, but from what I learned from Elias, it seems that this Crovey algorithm is there is not much problem with Crovey algorithm. Okay, thanks. So it just performs very bad when n is large, and we want to optimize this.
Yeah. All right. Okay. I guess. Yeah. I mean, just wanted to say that. Yeah. So, like, if you have questions, just feel free to unmute yourself and ask them now.
It might be very ridiculous question, but in quantum state tomography, we usually consider the case where samples is IID. So does there exist some work that consider non-IID case?
Does it exist algorithm for non-IID case?
Yes.
Maybe I think there is something called quantum online learning where it's kind of like you're given a state, and the person who gave you the state is kind of an adversary, and he kind of try to minimize, kind of modify the state and try to avoid you to learn to learn a state. So maybe the quantum online learning case is what you have in mind, I guess, when the state is non-IID.
Guys, I will check that definition.
Pardon?
I just mentioned that I will check that definition. Thank you for your answer.
On a similar vein, maybe like kind of more concretely, like along the same lines, what if you have you considered the situation where instead of having like row tensor n, you have a symmetrized state? So you maybe you got some you know, row 1, tensor row 2, tensor row 3, where they're different, potentially a little bit different, and then you've gone through and symmetrized it a bit like how you would do in like yeah, and then you get this kind of symmetrized state, which could have I guess entanglement across the copies, like a little bit of entanglement across the copies. Would your approach still work? Because it seems like, I mean, the main assumption there is that each of the permutation components is like identity divided by the dimension, right? It seemed like that was your main assumption, and I guess that would still hold under a symmetrized thing, would it? Is that correct?
Right. Yes.
So would anything break?
So, I don't think anything break. So if you have kind of maybe you may imagine that you get some different state for each copy, but maybe you get some average state for that. So this should be equivalent to that you get some average state on that copy, and then I don't think things will break.
Well, I guess one thing that would break is like, you know, you're trying to add a copy of the state every, you know, like you're doing this ladder thing where you add a copy of the state, but that doesn't really make sense in this global picture.
Well,
because you have to symmetrize somehow or something.
Well, for the space, they are always equivalent, so you could always do that part. So I guess it will be equivalent to that you perform the thing on all copies, but maybe something breaks. So it's kind of equivalent to you get row 1 tensor row 2 until row n, and then you perform a measurement on the on the symmetric subspace to learn it. So I guess when you perform the measurement on the symmetric subspace, it's kind of like equivalent to you symmetrize them a little bit. So if you first look at the if you don't look at it as a streaming way, you look at the unitary you applied on all the copies as a whole, then from that sense, it might not break that much.
Okay.
Okay, thanks.
Okay, thank you.
All right.
Thanks.
So, yeah, just checking if there's any more questions or comments from anyone else. Okay. I'm not seeing anyone.
Can I just ask a clarifying question, a kind of basic one? So when you maybe just focusing on the first half of the talk where you're doing the strong Schur sampling on the unitary component, so you measure your lambda, you project it onto a particular lambda, and then you want to like project onto the unitary component of the tensor product. And there you then like do some measurements, you know, you construct this fancy POVM and do some measurement. And so there, like are you basically doing tomography, like full state tomography on this state, like row that's in this subspace, or what is that? Can you say conceptually what you're doing there?
Right. So once you get the kind of the state on the Q lambda d subspace, it's the next step is you don't do full tomography on this on the state of this subspace, because you already know it is a state that satisfies some property, which means it is an element from the general linearized group. So you can make the group structure so that you can know more about it. Maybe I will go to the POVM element to illustrate more. Okay, so basically you perform this POVM element. So this POVM element means you know that so the
you know the spectrum. That's
right. You know the spectrum, right? And also you know that it is kind of so for this Q lambda D subspace, any state on this subspace, it has a much larger unknown variable than this U lambda bar U tensor, U lambda bar U dagger, because this U, it only has unknown elements in which is D squared, but for an arbitrary state on this subspace, the unknown variable should be D to the power of N, something like that. So you have already used the structure of this state to.
Wait, but that's like it's D to the power of N on the full system, but when you project it onto a particular lambda, then it's not D to the power of N anymore, right?
Right. So that's why we use the group structure, the group structure, because we know this the unknown element of this U lambda bar U dagger, it is only D squared. But if you do full tomography for a state on this Q lambda D, is kind of.
If you maybe I'll ask it this way: if you knew it was a rank 1 system, so then
Yes.
you're like you could do full tomography on a rank 1 system, and then instead of costing you D squared, it can cost you it costs you dr, right? So an r is 1. So is it the same in that setting as doing full tomography?
So by full tomography, you mean you just get a state on this subspace, and then you do full tomography on the state of this subspace?
Yes.
Or you, right? So yes. So in that case, when r equals to 1, you for a state on this subspace, you just get, which is the dimension of the subspace times the rank of the state. So the dimension of this Q lambda D subspace could be very high. What I mean was that.
Oh, okay.
So what I mean is you already make use of the kind of the group structure, like you already know this thing, and you know there is a map from this U lambda bar U dagger to the to this Q lambda subspace.
Okay. Okay. Thank you.
Thanks.